So last week we discussed weighted graphs and we solved problems like finding shortest paths between vertices using Dijkstra's algorithm and finding minimal spanning trees using Kruskal's algorithm. This week we're going to be concerned with adding arrows to our weighted graph, so we get what's called a weighted digraph or a network in which we have both weights or numbers assigned to the edges and each edge has a direction. And there are a number of practical problems that this object is useful for, and they're discussed in section 9 of the notes. But what I've decided to do in this online course is concentrate on flows in networks. So sections 9.1, which deal with activity networks, or what's sometimes called critical path analysis, you won't need the theory of that. Similarly, you won't need the theory of dynamic programming in section 9.4. I prefer to go into a little bit more depth in the study of network flows. Some of the techniques are similar, and what I want to do today is introduce the concept of a flow in a network. So this corresponds to 9.2 in the notes. So the basic idea is this. We have now not just a weighted graph, but what's called a weighted digraph. So we've already seen digraphs, but now we're going to put numbers, positive numbers, typically integers, on each edge, one number on each edge. So we have, I'll use the notation, so each edge has a direction. So an edge now is an ordered pair, and I'll write, rather than write it in the sort of notation U, comma, V in round brackets, I'll typically write U arrow, U with the arrow going to V to indicate that the arrow goes from V to V. Now the number we assign to the edge, we're thinking of this as a sort of network. So it might be a network of roads with traffic flow, or it might be a network of pipes with gas flowing in the pipe and so on. But the important thing is in the mathematical setting, each edge has a direction. So the flow can only go one way along the edge or along the pipe, whatever it is. So you should have in mind one carriageway of a motorway in which all the cars hopefully are going in the same direction, and the flow would correspond to, I don't know, how many cars pass a traffic camera in 1 minute, that sort of thing, or gas flowing along a pipe. So speed of gas, I gather natural gas is about 30 meters a second, and obviously the quantity of gas you can get flowing along the pipe depends upon the diameter of the pipe. So that's the setup. So we have this network to begin with, and each edge has a capacity. And then we try and, well, there are other properties of this weighted digraph. In particular, there are two special vertices. One is called the source, and the point about the source is that all the edges leave the source, so all the arrows go away from the source. All the edges adjacent to S, all the vertices adjacent to S, and all have those edges, and the arrows all leave S. And at the opposite end, there's the sink, in which all the arrows go into the sink, which I denote by T. And there's another technical condition. We want to make sure that for each vertex in our network, that we can find a path leading from the source through that vertex to the sink. I should say an aligned path in which all the arrows are going in the same direction from the source to the sink, passing through that vertex, and that has to be true for any vertex. I won't refer to that condition again, but it's needed for some of the results. So now I want to give you an example, and the point is, given such a network with capacities, so each edge now has an arrow, and it has a number assigned to it, which is the capacity. And I'll try and indicate capacities inside circles, so because they form part of the network. So in this very simple example, which is identical to the one in the notes, the capacity of this arc from S to A is indicated by the number 5 in the circle. It's not a good example because there's a 5 on top, but the capacity of the edge from S to C is indicated by the 12 in a circle. And what we then try and do is add a flow to this network. So we have a network of pipes and we're trying to get fluid flowing through the network. And there are many different ways of doing this. We want to try and optimize the flow through the network. So we want to try and assign flows to each edge to get as much flow as we can from the source to the sink. And the flow, it's important to realize that the flow can change. We can adjust the flow. In these problems, the capacity is fixed. That's part of the sort of hardware. We can't change it, but we can adjust the flow that we flow through the network. So the convention I'll try and use is that the flow numbers, here they're in red and they're written above the circles. They're the things we can change and improve if possible, but they have to satisfy certain conditions with respect to the capacities of the network. So let's look at the conditions that these flow numbers, and I'll give the definition on the next slide. But what are these flow numbers? So the flow is going to be indicated by assigning a number to each edge. And what are the constraints on these numbers? Well, there are two constraints. The first is that you can't have more flow along the pipe than the capacity of the pipe. So in the first edge S to A, this pipe is at capacity because the flow I've assigned, which is 5, is equal to the capacity of the pipe. So this edge is what's called saturated. In fact, I'll put an S here for saturated. Because we can't get it, even if we wanted to try and get more flow along this edge, we can't. It's saturated. On the other hand, this edge going from S to C, that has a lot of spare capacity because we only have a flow of 3 units, whereas the capacity is 12. So if you look at all the edges, you'll see that I've never put more flow on the edge than the capacity permits. Here we have another saturated edge. We've taken the maximum flow possible, but on all the other edges, we could, if we're able to, increase the flow because there's what's called spare capacity. That's the first condition. The second condition is that for every vertex other than the source and the sink, apart from those two vertices, the flow coming in, the sum of the flows coming in has to equal the flow coming in, if you like, is equal to the flow going out. By that I mean that the sum of the flow numbers on edges coming into the vertex is equal to the sum of the numbers leaving the vertex. And that's also true. Here we've basically very simple networks. We only have to check 3 vertices. We have to check what happens at A, what happens at B, and what happens at C. Because this is not going to be true at the source or the sink. At the source, everything is leaving the source and everything is going into the sink. But at these other 3 vertices, if you look at it, the red flow numbers satisfy that here we've got 5 coming in, 1 plus 4 going out. So that's okay at A. At B, we've got, what have we got? We've got 1 coming in and 1 going out, 0 here, so that's okay. And at C, we have 8 going in because these vertices are all going in, these edges are all going into C, and we have 8 leaving C in this direction here. So the condition is satisfied at C. That's a sort of conservation of flow. Inflow is equal to outflow, one could say. If we had an electrical circuit, this would be known as Kirchhoff's law for currents. Although that situation's a little difficult because here we have directions and we're specifying the direction in which the current can flow, but it's a sort of Kirchhoff's law. Now, the question is this flow that I've written here, is this a maximum flow? Okay, is the red numbers which I've assigned, I'm just hoping to get rid of them, is this a maximum flow? So forget all the scribble, just look at the red numbers. And what is so what I mean by maximum flow? Can we get, there's the concept of the value of the flow. So here we've got a flow of 5 plus 3 leaving the source, and that means the value of this flow is 8. Okay, the value of this red flow is what is called 8. What is called the value is equal to 8 in this case, because we have a total of 8 units leaving the source. And if you divide, any way you divide the network, the net flow is going to be 8. In particular, when we get to the sink, there's also 8 coming into the sink. It's a different way. It's coming along one edge, but it has to be because of the conservation of flow. The flow leaving has to equal the flow arriving at T. So the question is, can we get more than 8 units? Satisfying the constraints I mentioned, can we get more than 8 units? And the answer in this case is yes, we can get a little more, and I'll answer that. It would be fairly obvious if you could sort of stare at the diagram. In fact, you could pause the video and ask yourself, how would you get more flow satisfying the rules I've just given you? So this red flow, the red numbers, they do not constitute what's called a maximum flow. We can get a couple more units actually, and that's fairly obvious in this simple flow diagram. But I want to explain how we get that theoretically. So let me now write down the rules I've just told you for the flow. So for the flow numbers. So let me remind you that we're always given a network with capacities already assigned. They never change in the problem. They're assigned to each edge and they're positive numbers. Because this is a weighted digraph, and by definition of weights, they have to be positive numbers. Typically, they'll be integers, but they don't have to be integers. Depends what units you're using, obviously. Now, a flow, to define a flow, we need to also define numbers. So each edge gets another number, which is the flow number. So flow is a function from the set of edges to the non-negative real numbers. And we assign to each arc a flow number. And here are the two conditions which I already told you about. First of all, the flow could be 0. We could always start with the 0 flow. If I just take 0 assigned to each edge, that is a flow. So the 0 flow is possible. So in contrast to the capacitors, the flow numbers could be 0, or some of them could be 0, but they can't be more than the capacitor. They are at most equal to, each flow number is at most equal to the capacitor. And then, as I said, at each vertex, other than the source or the sink, so I'm not talking about the source or the sink, the flow coming in is equal to the flow going out. So here the picture is I've got a vertex V, and I've got a number of edges coming into V, one or more edges coming into V, and one or more edges going out of V. And let's suppose that X is an edge here coming into it. Let's suppose that X is an adjacent vertex with an edge going into V, and Y is an adjacent vertex to V with an edge coming out of V. Okay, so for when we add up the flows coming into V over all such vertices at X, the sum has to be the sum of the flow numbers which I'm assigning on the edges, which I haven't written here, has to equal the sum of the flow numbers on the edges going out of them. That's what you might call conservation of flow. Now, another convention that's important, whenever I write C of UV or F of UV, the notation implies that the edge is oriented. I'm thinking of round brackets UV as an ordered pair. So that means this is an edge with the orientation U goes to V. The arrow goes from U to V. If I write C of UV or F of UV, I'm implying that the arrow is going from U to V. If it's not, I'd write C of VU. Okay. Now, when you're talking about flows, you could get around this problem by defining F of VU to be minus F of UV, but I won't be doing that. My flow numbers will always be non-negative. I'll always make sure if I write F of UV, I mean that the edge has its arrow from U to V. That will avoid making mistakes. So I've been careful when I write this formula here to follow that convention. So here we've got the arrow going from X to V, and here we've got it going from V to Y. Okay, so those are the rules of the flow. And let's apply that. Well, let me continue by saying that I also talked about the value of a flow. So given a flow, it has a value because it succeeds in flowing fluid from the source to the sink. And the amount of flow leaving the source, the sum of the flow numbers leaving the source, is called the value of the flow. And because of conservation of flow, that will equal the sum of the flow numbers entering the sink. Indeed, if you divide the network in any way, and I'll show you the example in a moment again, you divide the network in any way, the net sum of the flow numbers, the flowing one way plus flowing backwards minus, the sum of those with the signs will always be the value of the flow. But so you can easily find the value of the flow by just adding up the sum of the flow numbers leaving the source. That is the value of the flow, and that's what we're trying to increase. Given a network with capacities, we want to know what is the maximum, what is the maximal value, or to find a flow which realizes this maximal value for the flow. Obviously, that's going to be bounded because the pipes are finite numbers and we can't get infinite flow from the source to the sink. So that's the problem. So we want to find a maximum flow, and in particular, this will mean that some of our arcs, one or more, will be saturated. Otherwise, if there weren't, if none of them were saturated, we could certainly get more flow from the source to the sink. So now I want to give an idea of the labeling algorithm, which is the thing you use to try to increase flow and find maximum flow. So the idea in this problem now, it's getting a bit complicated, but we have a weighted digraph which corresponds to our network with capacities. There's also a source and a sink, as I mentioned, but we have these capacity numbers. And then what we want to do is we have a flow as well on top of that network. We've assigned a flow to that network. It could be the zero flow. We could always start with the zero flow if you want. But we have this network of pipes and we have some fluid flowing through it. We want to increase the flow of that fluid. Okay, and we do that by what's called augmenting or increasing the flow. And we do this sort of vertex by vertex, edge by edge. And I want to give you the idea. That's going to lead to something called the labeling algorithm. I'll be talking in more detail about this in the third video. But I want to give the idea already from the start today. Obviously, you can read more details in the notes. But the idea is this, that we use what we sort of learned before about like breadth first searches. We're going to search this network using a sort of breadth first search, starting from the source. A breadth first search means basically we scan all adjacent vertices. So starting from the source, we look at all the adjacent vertices and we try and increase the flow along them. But of course, until we get to the sink, we don't know we can increase the flow. So we sort of put temporary labels on vertices to sort of, as we go along, to tell us where we might be able to increase the flow. So we're going to start with the source, but then we keep adding vertices. So at a given point, we'll have a given vertex. It's like in Dijkstra's algorithm, and we'll be scanning the other vertices. So in Dijkstra's algorithm, we made a vertex permanent, and then that scanned other vertices that were adjacent to it, vertices that hadn't already been scanned. So suppose we're at such a vertex, which means really it's come to the front of the queue. We call it here V. Suppose we have such a vertex and we use it to scan other vertices. So we're now, if you like, V is the current, in the jargon, V is the current vertex. It's come to the front of the queue and we want to use it to scan other vertices. So maybe we have our vertex V and we have vertices, two vertices which are adjacent to V. We might have a vertex X. We probably have more than two vertices, but suppose we have in particular two vertices adjacent to V. But you see, with our arrows, there are two different types of edges, as I've mentioned already. coming to a vertex. There are the arrows that go into the vertex and the arrows that go out of the vertex. And there may be other ones as well. But you have to treat these two different types of edges separately. So somehow the easiest ones to treat are the edges in which the arrow goes away from your current vertex. So here's the current vertex. So if we have an arrow going from V to Y, then we won't necessarily see all the vertices. Maybe we've got a Z here. So for example, if this particular edge here going forwards to Z was saturated, then V would not actually see Z. We wouldn't do anything with Z. So unlike a normal breadth first search in which we look at we see all the adjacent vertices imagined to the Q, we won't do that if, for example, this forward going edge is saturated. Its flow number, I'm not going to put the numbers here in this little mini diagram, but if the flow number equals the capacity, this will be saturated, and effectively we wouldn't see this edge. It's like if it's saturated, we just don't see it. Okay, so we only see edges going forward if they're not saturated, if they have spare capacity, if the capacity minus the existing flow is positive. And then we see Y and we add Y to the Q. So we'd sort of have V and we'd add Y to the Q. As regards X, because X has its edge coming into V, there's a different rule for that. We only see X if there's already non-zero flow coming into V. So irrespective of what the capacity is, we want non-zero flow coming into V. In that case, we see X and we put it on the Q, or we might have done it in the other order, depending on probably X comes before Y, so we'd have probably formed the Q. We start the Q with S, there might be other vertices up to V, and then X and Y would be added like that. If these conditions here are satisfied. That's the idea. Okay, now I'm going to show you an example of how that works with our example network. Okay, so what I'm going to do now is I'm going to do the so-called labeling algorithm, and I'm going to do what's called one iteration. So what that means is, remember, we've got a flow here of value 8. Our existing flow, we have an existing non-zero flow and its value is equal to 8 because the sum of the flow numbers coming in to going out of the source is 8. In fact, if you cut the vertex in any way, you'll find that the net flow going across the network is 8. I mean, the way I've cut it here, you've got +1, -1, +8. So the sum is 8. That's the idea. Okay. So the value of this flow we've already assigned here, is equal to 8. Not that too much. The value is 8. You also see that by looking at the 8 going into the sink, as I mentioned before. The sink of 2. Now let's just form this Q. Let's do what I said. So what we do is we start with S, that's the source, and the theoretical reasons, because we're going to have a formula in the last video, which was a bit like when you apply Dijkstra's algorithm. If you want to do it formally, there's this relaxation formula. So we should really put a label of infinity under S, but it doesn't really matter about that today. So then what do? We look at the vertices that are adjacent to S. And what do we see? We see that one is saturated. So because that's saturated, we don't see A. Okay. So in the Q, when we do our Q starts, I've written here what it's going to be, but let me do it by hand, fresh. So the Q starts, so here's our Q. I'll just capital Q. Q. The Q starts with S. And we don't see A, but we do see C, because C has spare capacity. Okay, it has a spare capacity. The arrow is going forward. All the arrows from the source will go forward. And we have a spare capacity of 9. So what we write under C, so C is added to the Q. We've already added S. We're now going to add C. Here I put the vertices along the top in order. in alphabetical order, apart from the sort. The source always is first and the sink is always last, but in the middle I put them in alphabetical order. But that's not necessarily the order they join the queue. So in this case, C joins the queue after S because A was not visible. And C gets given a label. It's a bit like in Dijkstra's algorithm. So the label it gets given, the numerical label, is the 9, because the 9 comes on as 12 minus 3, because that's the spare capacity. Okay, 12 minus 3 is the spare capacity of the edge AC. So that's fine. So we put C on the queue. Now we've dealt with S, and we now look at C. So when we look at C, what do we see adjacent to C? Well, there are 2 vertices adjacent to C. So C can see both A and B. It doesn't, by the way, see T because this edge is saturated. But it can see A and B, but the edges coming into C, they come into C from A and B. But they both have non-zero flow. So as far as A is concerned, it can see A, and the label we put is we don't care about the capacity. This is irrelevant, really. What is relevant is the flow. The flow is 4, and we can reduce that to 0. So the numerical label in this situation is the 4. It's not the spare capacity. This edge is actually saturated, but that's irrelevant. It's irrelevant that this edge is saturated. What's relevant is the fact it has non-zero flow in this case. And so what we do is we put the flow we can reduce to 0, and that's 4. And we put the C because it's coming A. We're labelling A effectively. Before we labelled C, now we're labelling A, and we can reduce the flow. So in some sort of net sense, the flow is coming from C. So we put where it's emanating from, that C, and minus to indicate the fact that the arrow goes into C, goes away from A. And we do the same thing for B. Here the 10 is irrelevant, the 1 is relevant, so the numerical label becomes a 1. So the point is we can somehow increase, in some sense, the flow to B by capping off the pipe. So we were losing, think of this as leakage here, we were losing 1 unit from B to C, but if we cap off the pipe, then we're essentially increasing the flow to B. So the flow to B is actually being increased by 1. And then A, now we've already added B and C to the queue. So sorry, we've just dealt with C. We can then deal with A immediately because A doesn't see any new vertices. The vertices adjacent to A are B and C, but they've already been dealt with. So they're already in the queue. So we don't put them again in the queue. So we move on to B, and B sees T, and there is spare capacity here. So there's a spare capacity. B sees T, so T goes on the queue, and we're finished. Once we get to T, we're finished. We have spare capacity of 8, but the 8's useless to us because as far as B is concerned, we could only get extra flow of 1. So we're only going to add a 1 here. The 1 here is really added because it's the minimum of the spare capacity, which was 8, or rather 8 minus 0. That's the spare capacity. But the flow we could already increase to B, which is 1. That was the label which we already had on B. If you like, the 1 really was the label we had assigned to B. So we take the minimum of those, which is 1, and that's the flow we can actually, because that's the extra flow we can get to T. We can't get more than 1 because we've only increased the flow of B to 1. So what we've managed to do here is we've managed to increase the flow from S to T by 1 unit. This 1, I'm also going to call it epsilon because it's the flow we're managing to get from A to T, the extra flow we can get from S to T. We were able to get this flow of epsilon, an extra quantity, epsilon equal to 1. Well, that's a bit breathless, but that's one application of the labeling algorithm. Now that, in fact, only increases the flow by 1. In this example, one could have increased it by an extra 1. We can increase it by 2, actually. So we now sort of adjust our flow, which I'll do now, and then rub everything out and do another iteration, which I won't do in detail. But let me at least tell you how to adjust the flow by what we've just done using the labels in this first iteration. Let me explain that now. What we do here is we just remember, we take what's called the winning path. So how do we get the winning path? Or really the correct word is augmenting path. I like the word winning path. So the winning path, you see, we start with T. We look at the label underneath T. We look underneath T and we see that the path getting to T came from B. The extra flow, I should say, came from B. Okay, so the epsilon here is 1. So we're going to increase somehow the flow from the source to the sink, as I said before, by 1. So the 1 is going to arrive at T along this edge. So this 0 becomes a 1. We add the 1 to that edge because it was a forward edge. Here's 2. Then we trace back to B. Of course, here we can remember it all, but strictly speaking, we use the table. We trace back to B. So we look and see what happens for B. And B got its extra flow by capping the edge. Minus tells you capped the edge from B to C. So what that means is that we removed the 1 on this edge. So this 1 becomes 0 because we capped the edge and blocked it. So there's no flow going from B to C. That effectively increased the flow to B. What it really meant is we just simply diverted the flow. Whereas before it was coming this way, the 1 unit was going to 1 unit. Now it's going across to T. The 1 is going to T. So the flow this time is going that way. Okay, so we remove the 0 here. And then, of course, the C, we look at the C, the flow, how did we get the flow to B? It came from C. And then we look and see what C is labelled with, and the C is labelled by the 9 coming from S, but all we do is add 1 to that. The 3 doesn't become a 1, it becomes a 4. We've added 1 to the 3, it becomes a 4. So we've got 4 plus 4 is equal to 8, so we still have conservation of flow. So in other words, what I did here is I simply adjusted the flow numbers by adding 1 when there's a forward arrow, subtracting 1 when there's a negative arrow, and adding 1 when there's a forward arrow. So this 0, just repeat, this 0 became a 1, this 1 became a 0, and this 3 became 3 plus 1, which is 4. Okay, that's how you adjust the flow. We've now got a new flow, and we can just start everything again. We just rub everything out and start everything again. Now, if you look at this diagram, you can see now how you could get a bit of extra flow across this network. If you look along the top, you see if we could convert this 4 to a 3, then we could push 1 extra flow along the top, and we could actually continue that from B to T. We'd still be satisfying the rules here, because 5 is equal to 3 plus 2, so we're satisfying conservation of flow at A and also at B. But we're now getting, I've got to adjust things here because the 3 is being cut off there, so we can now get 1 extra unit. The 4 can become a 5, and we can get 1 extra unit from S to C because I reduced this edge here, so I can add 1 here. So it's like, again, diverting the flow by 1 unit, getting 5 along here rather than 4. So if you look at everything now, you'll see that I've now got a flow of 10 because I've got 10 units leaving S. All the rules are satisfied. So in fact, the maximum value, if you like, in this example, is equal to 10. Now I sort of cheated a bit at the end once I just did it by inspection. But what one could in theory do, and you would have to do in a more complicated situation, is apply another iteration, like the blue iteration. Having adjusted the flow numbers as I did, you then apply a second iteration And you would see that what would happen is that the edges would be adjusted in this way. And so you'd end up with this flow, this maximum flow with value 10. Okay, now I'm running out of time. I have already, I'm afraid. But let me just finish by showing you how that works. So I've actually done the second iteration here as I did the first, so I want you to check that yourself. Things will work slightly differently, but you'll see you'll still end up, this edge here, of course, is saturated, so any extra flow to T is still going to come along this edge here, but you'll be able to get that extra unit coming from B. But this time, if you go to B, you see that it doesn't come from C, because we already changed these numbers, by the way. This was a 1, I haven't updated it. This was a 0, and this was a 4. That's where we started from. I should have done that in red as well. But anyway, we can get an extra flow from A, so we can make this. I won't repeat what I said before, but you can change the numbers. Maybe I will actually. You can change this. If you look at this second iteration, following the rules I did before, you get the second iteration. And if you look at you start at T again, there's 1 coming from B, so that means the path, the path, which I'll write down in a moment, you'll see the text, is, first of all, it's coming from B, so this 1 becomes a 2. And then if you look at the B is coming from A, so this 1 becomes a 2. And then A is coming from C minus, so that means this 4 becomes a 3, you subtract 1. And then finally C is coming from S. Spare capacity is 8, but we only got 1 for changing, this 4 becomes a 5. Okay, and that gives us the maximum flow. So we've obtained a maximum flow, and that's how it works. Okay, I've got the right numbers in again. So the final maximum flow, just rub out all the old flows. So at the end, what we've done is we've got 2 units across there. We've got 0 here. We've got 3 here. We've got 5 here. Not 3. 2 here. This stays as 5, so it's saturated. This edge is saturated. This stays as 8, so this edge is also saturated. So in some sense, we can't use it anymore. And that gives us our maximum flow of 10, which you can think of as either 5 plus 5 or 2 plus 8.